Okay, here we are discussing about the thick cylinder and its design of thick cylinder is discussing here. Okay, what is thick cylinder? Thick cylinder means the thickness is more. When the ratio of inner diameter of cylinder to the wall thickness is less than 15, it is called a thick cylinder. That means di by d. Di means inner diameter of the cylinder divided by thickness. If it is less than 15, it is called a thick cylinder. That's it. Then difference between thin cylinder and thick cylinder. When considering the stresses coming on it, or considering the stresses for the design, what are the differences between thin cylinder and thick cylinder? In the case of the thin cylinder, it is assumed that the tangential stress, here it is the hoop stress itself, we assumed that it is uniformly distributed over the cylinder wall thickness. That means you consider this is the cylinder cross section, the inner diameter and outer diameter. Inner diameter and outer diameter. In the case of thin cylinder, the hoop stress is assumed that it is distributed uniformly across the section. That means the hoop stress here at the inner radius or small radius it is, and the hoop stress in the outer radius or outer surface, inner surface and outer surface are the same. The hoop stress here, here and here, in all these area the cross section, hoop stress is constant. It is uniformly distributed. It is assumed so in the case of the thin cylinders. But in thick cylinder, the hoop stress is maximum at the inner surface. Inner surface is maximum. At the inner surface, the hoop stress is maximum, and it is gradually decreases and become minimum at the outer surface, as the distribution showing here. This is the distribution of the thick cylinder. Okay, in the case of thick cylinder, it is maximum at the inner surface, and it has been decreasing and become minimum at the outer surface in the case of the thick cylinder. That is the basic difference between the stress distribution of thin cylinder and thick cylinder. Okay, that is the first case. The next point is the radial stress sigma r is neglected in the case of the thin cylinder, but radial stress sigma r has significant magnitude in the case of thick cylinders. In the case of the design of thin cylinder, sigma r is neglected. Sigma r, in the radial direction, in this direction, that load, the hoop stress is perpendicular, or that is known as the tangential load, etc. That is, so we are taking the projected area in the case of the hoop stress. The stress in this direction, arrow mark showing the direction, in this direction shows the radial stress. That radial stress is negligible in the case of the thin cylinder design. We are not taking the sigma r at the time of designing the thin cylinders. But in the case of the thick cylinder design, it has a significant magnitude that has to be taken into account. Sigma r has to be taken into account. Sigma r design. These are the basic differences between thin cylinder and a thick cylinder. Okay, that stress distribution is showing here. Then, during the design of thick cylinders, 3 equations are used. 3 equations for the different conditions are applicable. For example, if the material is brittle, if the cylinder material is brittle like cast iron, we can use Lame's equation. It is available in our data book, PSG data book 6.15. Okay. The condition is that Lame's equation can be used if and only if the material is brittle. The best example is cast iron. If it is cast iron, you can use this equation for the designing. This is the Lame's equation. T by Ri. T means thickness. Ri means inner radius. 1 plus Pi. What is it? Pi? Internal pressure inside the cylinder. Pressure inside the cylinder is the Pi. Then sigma. Sigma means permissible stress of the cylinder material. Okay, sigma is the permissible stress. Then Pi sigma. It is whole raised to half minus 1. Okay, these are the parameters. Anyway, this formula is available in our PSG data book 6.15. This is the book. This is the corresponding page 6.15. This is the formula. Anyway, the Lame's equation is based on the maximum principal stress theory. Okay, maximum principal stress theory. This equation is here, maximum principal stress theory. Lame's equation itself. Okay, this equation can be used for the designing of the thick cylinder if the material is brittle. The material is brittle. Okay. Next case. If the material is ductile and its ends of the cylinder are closed, both ends of the cylinder are closed. The condition is that material should be ductile and their both ends are closed. In that case, we are using another equation, Clavarino's equation. Clavarino's equation can be used. This is also available in our PSG data book. Here T by Ri, we know T is thickness, Ri means internal radius. Here 1 plus 1 minus 2 nu. There is another term, nu. Nu is nothing but Poisson's ratio. Okay, nu is the Poisson's ratio of that material. Then Pi by sigma. Pi we know that is the internal pressure. Then sigma is the permissible stress of that cylinder material. Okay, all these terms are under the root, square root, that is raised to 1 by half, minus 1. Then the corresponding formula can be taken from the PSG data book 6.16. This is the corresponding page. That page is here, given here. This is the formula. Anyway, Clavarino's equation is based on the maximum strain theory. It is based on the maximum strain theory, and that equation is available in the data book. Maximum strain theory. Okay, this equation can be taken for the design of the thick cylinder. ഇത് ഉപയോഗിച്ചുകൊണ്ട് നമുക്ക് thick cylinder design ചെയ്യാനായിട്ട്. Okay, പറയുന്ന condition ഉണ്ട്. Condition is that the material should be ductile and both ends of the cylinders are closed. Both ends of the cylinder are closed. രണ്ട് closed condition ആണെന്നുണ്ടെങ്കിൽ അപ്പോൾ engine cylinder പറ്റുമോ? No, it is not possible because its one end is closed, other end is moving, or other end is not in a fixed position, is moving. So in that case it cannot be used. Clear? Clavarino's equation. Third one is Birnle's equation. Here the condition is material should be ductile. It is applicable when the thick cylinder is its material is ductile and end is open. One end is closed, okay, but other end is open. In that condition, we can use another equation. This is the Birnle's equation. Birnle's equation it is very similar to that of the Clavarino's equation. Clavarino's equation പോലെ തന്നെയാണ്. Okay, പക്ഷേ ഇത് ഉപയോഗിക്കുന്നത് എപ്പോഴാണ്? വൺ എൻഡ് ഓപ്പൺ ആണെന്നുള്ള സമയത്ത്. ഡക്റ്റൈൽ ആയിരിക്കണം, and other end is open. One end is closed, other end is open. Its denominator is same as that of the Clavarino's equation. There is no change. Here is also a small change. Instead of 2 nu, to see the Clavarino's equation, here 2 nu. Okay, instead of 2 nu, here we are using only 1 nu. One end is closed, only one end is closed, the other end is moving. In that case, Instead of 2 nu, we are using single nu. This is the only difference between Clavarino's equation and Birnle's equation. This is based on the maximum strain theory itself. Clavarino's equation is based on the maximum strain theory. Then Birnle's equation is also based on the maximum strain theory. Okay, but in that case both ends are closed. Here only one end is closed, the other end is open. So here there is some difference in the formula. Here instead of 2 nu we are using only 1 nu. Okay, that is the only difference. Keeping into mind these conditions, we can solve the problems. There are 3 conditions. The first one is the material is brittle. In that case we are using Lane's equation. Material is brittle. If the material is ductile and both ends are closed, we can use Clavarino's equation. If the material is ductile and one end is open, we use Birnle's equation. Okay, then design can be done. Take the first problem. Namta problem. The piston rod of hydraulic cylinder exerts an operating force of 10 kN. Force is given. Force inside the engine cylinder is 10 kN. This force is means force due to the combustion of air fuel mixture. Clear? That is the gas pressure. Due to gas pressure some force will be there. That force is 10 kN. In addition to that, the friction due to piston packing and stuffing box is equaling 12% of the operating force. In addition to this 10 kN, there is additional frictional force. In addition to this one, this 10 kN, there are some frictional forces. That is 10% of this one. 10 kN 12% കൂടി വരും force വരും. Okay. Then pressure in the cylinder is given as 12 megapascal. Inside the engine cylinder force തന്നിട്ടുണ്ടല്ലോ 10 kN. Okay, but the inside pressure is also given 12 megapascal. 12 megapascal or Newton per mm square is given. The cylinder is made of CIG 2000. That is the material. This is cast iron. You know, CIFG cast iron. You know, cast iron 200. It's a sigma U. Sigma U means ultimate stress is given 200 megapascal. The permissible allato. It is the ultimate stress. And the factor of safety is 5. Then the factor of safety engine up factor of safety in 200 by engine alpha permissible. Determine the diameter and the thickness of cylinder. Diameter on a thickness. A very simple problem. Can be expected for the given details. Pressure inside the cylinder is 12 megapascal. Megapascal means 12 Newton per mm square. Megapascal is nothing but Newton per mm square. Then factor of safety is 5. The permissible stress, the ultimate stress sigma U is given as 200 megapascal. It is given in the problem itself. That means 200 Newton per mm square. Megapascal means Newton per mm square. Then we can start it. We know that the total force of piston, total force acting on the piston, 10 plus 1.2. What is 10? 10 is the force inside the cylinder. In again, here there is some frictional forces that has to be taken into account. Totally 11.2 kilonewton is exerting on the piston. This much force. Total force is 11.2 kilonewton. Okay, that total force is equal to the inside pressure into inside area, cross-sectional area. This is the cross-sectional area into pressure. This 11.2 is the total force. that force is also equal to the inside cross-sectional area of the cylinder into inside piston, inside pressure, inlet the pressure inside the cylinder, PI. Both are equal. Pi by 4 d square, that is the cross-sectional area, into PI. PI is the pressure. This will be equal to 11.2 kilonewton. Then total force equals 11.2 into 10 raised to 3 Newton. This 11.2 kilonewton means into 10 raised to 3 Newton. Then here the known values are given. Pi by 4 di, it is unknown. At the same time PI is nothing but 12 Newton per mm square, that is given here, 12 Newton. The only unknown is now di. Di can be calculated from this relation as 34.47 mm, that may be rounded into 35 mm. Now inside the diameter of the cylinder is designed as 35 mm. That is one answer. Then we have to find out the thickness. Thickness of the cylinder has to be designed. Here we know that the material is cast iron, that is brittle material. Since cast iron is brittle material, the suitable or applicable equation is Lame's equation. Lame's equation is applicable. This can be used. So ഇതിനകത്ത് cast iron ആയതുകൊണ്ടും that is brittle material. In the case of the brittle material, the most suitable relation is Lame's equation. That is taken. That is given in the PSG 6.15. PSG 6.15 the data book in the page. And it is written here. T by Ri. T is the thickness that we have to be find out. Ri. Ri for നമുക്കറിയാം. Di is 35 mm. ഇതിന്റെ പകുതി അല്ലേ? That is 17.5 എന്ന് കൂടെ കൊടുക്കാം. Then 1 plus PI. PI means inside pressure. That is 12. It is given in the problem itself. Okay, 12 Newton per mm square. That can be given here. Then sigma. Sigma is the permissible stress. Actually, the ultimate stress is given in the problem as 200 Newton per mm square. And the factor of safety is 5. Then what is the permissible value? 200 divided by 5, 40. Here sigma will be 40. All these items can be given. Then we can find out the only unknown is T. Yes, this again written as, this again applied here. T has to be find out, thickness, divided by Ri. Ri means 35 is the diameter, it's half of that diameter, 17.5 equals 1 plus PI. PI means 12 Newton per mm square. Inlet, the pressure inside the cylinder is 12 Newton per mm square. That 12 is given here. Then sigma is 40. Then 40 200. There is factor of safety. Okay, 200 ultimate stress ആണ്. Ultimate stress ആണ്. Then permissible stress means ultimate stress divided by factor of safety. 200 by 5, 40. 200 by 5, 40 is given here. Then 1 minus 12 by 40. All are under the root. Raised to half. Minus 1. On calculation, you will get the answer T is equal to 6.348 mm. That may be rounded into 7 mm. Okay. Now that problem is over. Very simple problem.